Alright, so alkanes undergoes two major reactions. There are other reactions, but the two major reactions that alkanes do undergo. We have the first one, we have the addition reaction. And the second one we have oxidation reaction. So we're going to take them one after the other. We take addition reactions, or we take oxidation reactions. Alright. Now, what is actually going to differentiate addition reaction is basically the type of reagent that we're going to be reacting with this. Right? So in exams, they will not come and say addition reaction. No. They'll just tell you, okay, this is alkene is reacting with this. Now, based on the reagent, you're the one to know that, oh, this gets addition reaction. Now let's look at the various reagents that react with alkanes via addition reaction. The first one we have hydrogen. This is called hydrogenation reaction. The second guy we have halogen. This X stands for halogen. That's halogenation reaction. The third guy is hydrogen halide. The fourth guy is water. Array in history, but I'm not going to discuss this. Not that really very important. Okay. So whenever you react hydrogen with an alkane, that process is known as hydrogenation of alkane. Now, whenever you react halogen, remember this X is halogen. The X can be chlorine, can be bromine, or it can be what? Iodine. Now, the process where halogen is reacted with an alkane is known as halogenation. Now, this guy is addition of hydrogen halide is hydrohalogenation, and this guy is hydration. So take note of this. These are the reagents that react with alkanes via addition reaction. So in exams, they will not really tell you addition reaction. No, they will simply say, if the product of the reaction, when also alkane reacts with any one of these, once you see any one of these reacting with an alkane, of course, that should tell you that it is addition reactions of alkanes. I would like to explain some few terminologies or some few things here before we proceed, which is very, very important. Now, it is important that we understand what is referred to as unsymmetrical alkane, unsymmetrical alkanes, and unsymmetrical reagent. Now, these unsymmetrical alkanes and reagents, you need to understand this before you can understand pretty well how addition reactions of alkanes works. Now, these reagents I listed down here, some of them are symmetrical, while some of them are unsymmetrical. Symmetrical simply means that if you split it into two halves, what you're going to have on the left-hand side would be the same thing as what you're going to have on the right-hand side. That's symmetrical. Unsymmetrical means that if I split any of these reagents into two, the one I have on the right hand side, if it's not the same thing as what I have on the other side, that is unsymmetrical. So there are rules that guide when an unsymmetrical alkanes react with unsymmetrical reagents. That rule is called Markov-Nikov rule, right? So before I proceed to talking about Markov-Nikov rule, now we need to understand what an unsymmetrical alkanes are and what symmetrical are. As the name implies, unsymmetrical. For an alkane, alkene is said to be unsymmetrical, but when the two carbons of the double bond are not having same number of hydrogens. For example, we have something like this. I have this. Now the two carbons of the double bonds are the ones with asterisks. This one here is having two hydrogens, and this here is having how many? One. They are unsymmetrical. I have no business with whatever I have here. My interest is just between the two carbons of the double bond. Once you pinpoint them, how many hydrogen is attached on each of them? This guy is having two, this guy is having one. That is unsymmetrical. Now, if I have something like this is unsymmetrical. Now, how about if I have something like this? Now, this is symmetrical. This carbon is having how many hydrogen? This guy is having how many? Two. Take note of that. So this is actually what we mean by unsymmetrical alkene. They can actually put it in any form. There are some types that, let me also give us another example of unsymmetrical alkene. You can see something like this, CH3, C, CH3. This is another example of unsymmetrical alkenes. The two carbons of the double bonds are the one with the asterisks. This guy has no hydrogen, this guy has one. So this is unsymmetrical. Another example, I can do something like this. I can go on and on. This is still unsymmetrical. This carbon is having no H, this guy has two. So the two carbons of the double bonds are not having same number of hydrogens. So that is actually how you can tell if an alkene is unsymmetrical or if an alkene is symmetrical. Now, having said that, let's talk about reagents. And the reagents we are talking about are these ones here. Reagents. Please look up. Example of unsymmetrical reagents is number 3 and number 4. Number 1 is not unsymmetrical. Hydrogen is not unsymmetrical because hydrogen is H2, which can be written as this. If you split this into two, H on one side, H on the other side, they are all the same. H2, let's convert this guy to, let's say, bromine molecule. If you say Br, if you split this guy, this and this, they are all the same, right? So the two unsymmetrical reagents that we have here are the two unsymmetrical reagents that we have, HX and H2O. Because this guy is this. If you split this guy, you have H and what? X. They are not the same. Water is H, OH. If you split this guy, you have H and OH. That is how it is. Now, why am I doing all of this? Because there is a rule that actually guides addition of unsymmetrical reagents to unsymmetrical alkenes. Now, if you bring water, if you bring this guy and react this guy with an alkane, how the reaction proceeds. Okay? So we're going to look at that shortly. There is a rule that guides addition of unsymmetrical reagents to an unsymmetrical alkane. There is a rule that guides addition of unsymmetrical reagents to unsymmetrical alkenes, comma. This rule is known as Markov-Nikov's rule. The rule is known as what? Markov-Nikov rule. Please stop. Now, what is Markov-Nikov rule? Please do down. Markov-Nikov rule states that during the addition of unsymmetrical reagent to an unsymmetrical alkene during the addition of unsymmetrical reagents to unsymmetrical alkenes, during the addition of unsymmetrical reagents to unsymmetrical alkenes, the hydrogen of the reagent must add to the carbon of the double bond with more hydrogen. Markov-Nikov rule states that during the addition of unsymmetrical reagent to an unsymmetrical alkene, the hydrogen of the reagent must add to the carbon of the double bond with more hydrogen. We have CH3 physical. Now this alkene is unsymmetrical because this carbon here and this carbon, they are having unequal number of hydrogen. This is 1 and this is 2. This HBr is also unsymmetrical because if you split this guy, you're going to have H and what? Br. Now, if you have this type of addition reaction, first thing first, once you see HBr, oh, this guy is reagent for addition reaction. So this guy has to be added across a double bond. The next thing you're going to say is that, is the alkene unsymmetrical? If the alkene is symmetrical, there is no rule that will guide that addition. The H can add anywhere. But once the alkene is unsymmetrical, there is a rule you must follow, and the rule is the H must go to the carbon of the double bond that has more hydrogen. So these are the two carbons of the double bond. This H will come to this guy that has 2 hydrogen. The Br goes to the one that have what? Less hydrogen. This becomes CH3, CH, CH3, what? Yeah. That is it. If you do the opposite, the product you're going to have is not going to be the same. And you're going to fail that question. But assuming this guy is symmetrical, right? You can add it. Let's say, for example, if I have CH2 plus HBr. Yes, this reagent is unsymmetrical, but the alkene is symmetrical. There is no rule. Meaning that this H, if you add this H here and add the Br here, it's still the same thing, like adding it opposite side. That's what it means. Because if you add it here, it becomes CH3, CH to Br. This is bromoethane. You start counting from a 1, 2. If you do the opposite, come here, put the bromo here, and put it in the what? This is still bromoethane. So that is why, once the alkene, the reagent is unsymmetrical, alkene is unsymmetrical, you must follow the Markov-Nikov rule. Right? If you want to forget this guy, just remember Luke chapter 19, verse 26 that says, to whom that has, more shall be what? Given. Now let's look at the first one. The first reagent is HBr. I gave us 4 reagents, so let's start with this guy. So we have example. Please, HBr is an unsymmetrical reagent, just like I explained earlier. So anytime this HBr reacts with an alkene that is also unsymmetrical, you must adopt the Markov-Nikov rule. It's a must. So let's take an example. We have CH3. Now this is 2-methyl with 2-ene. 2-methyl with 2-ene, because if you start numbering from here, 1, 2, plus HBr Now the two carbons of the double bonds are the ones with the asterisks. As such, this guy is going to be used to determine if the alkene is unsymmetrical. This is having one hydrogen, this is having no hydrogen. So the number of hydrogens are unequal. As a result of that, they are unsymmetrical. These reagents, H and Br, of course, they are not the same. The hydrogen of this guy, you go to the carbon of the double bond that has what? More hydrogen. And which is this guy here. So this becomes CH3, CH what? 2. Please, you must always put the double bond at the end of the day. This becomes CH2. This is C what? You put your CH3 here, and you put your CH3 here. And that's the product of that. This becomes 1, 2, 3, 4. If you want to name this guy, it's obvious that we are going to number from this side. Now, bromo is at number 2, methyl is at number 2. B comes before N. So this is going to be 2 bromo, 2 methyl, what? Ethane. So that's the name of that product. Like I said, I don't have to take like 50 examples. I'm just going to do 2 examples here. And then we look at the anti-Markovnikov rule. Please, most of the time, this reaction is always carried out in the presence of an acid, alkanoic acid. So you can see something like CH3, COOH here. It's normal. This acid does helping us to fasten or hasten the process. It's doing the work of the catalyst. Alright? Okay. Now this is example 1. Now please, let's attempt the second guy. Now the 2 carbons, if you want to label this guy, this is carbon 1. You start numbering from the side that will give the double bond the smallest number. This is carbon 2, 3, and 4. Carbon 1 and carbon 2 are the 2 carbons of the double bond. And carbon 1 has 2 hydrogens. This guy has 1 H. You look at this guy is unsymmetrical, this guy is also unsymmetrical. As a result of that, you must apply Markovnikov rule. It says that the hydrogen of the reagents goes to the carbon of the double bond that has more hydrogens. And carbon 1 and carbon 2 are the 2 carbons of the double bond. Carbon 1 has 2 hydrogen, carbon 2 has 1. Please, this hydrogen on carbon 3 is not counted for carbon 2. So the H will add to carbon 1. We have CH3, CH2, and then a Br comes here. Now this becomes 2 bromo butane. So that's how the Markovnikov rule works. So I'm going to just take anti-Markovnikov rule. Please take note that they might decide to just put CH3COOH. This is acetic acid, ethanoic acid, right? Or they can use any other acid. So let's look at the anti-Markovnikov. Anti means opposite. Acid. Please look up. The word anti simply means that it's always opposite. So anti-Markovnikov rule is the opposite of Markovnikov. Now in Markovnikov, hydrogen of the reagent will always go to the carbon of the double bond with more hydrogen. Is it not so? What do you think will be the anti? Hydrogen will now go to the one that have what? Yes. Less hydrogen. Now, anti-Markovnikov rule must also involve unsymmetrical alkenes an unsymmetrical reagent. It's a must. Now, but something must be done to that reaction to actually make it to go through the opposite route. If somebody is supposed to pass through this road, all right, and then suddenly the person starts following another road, there must have been something done on that part, is it not so? So please put down, anti-Markovnikov is the opposite of Markovnikov. Anti-Markovnikov rule is the opposite of Markovnikov rule. And it states that when an unsymmetrical alkane reacts with unsymmetrical reagents, when an unsymmetrical alkane reacts with an unsymmetrical reagent, in the presence of a peroxide, please emphasis on the peroxide, that is a condition that will make this guy follow the anti-Markovnikov. When an unsymmetrical alkane reacts with an unsymmetrical reagent in the presence of peroxides, the hydrogen of the reagent adds to the carbon of the double bond with less hydrogen. The hydrogen of the reagent adds to the carbon of the double bond with less hydrogen. Sorry, is this in serious on the back? The hydrogen of the reagent adds to the carbon of the double bond with less hydrogen. All right. Now, what are the examples of peroxides? Examples of peroxides that you're most likely going to see, we have the first one, hydrogen peroxide, which can be written as, the normal one you guys know, can be written like this, or they can write it as this, or they can write it as. Now these are the possible ways they can write it. Now hydrogen peroxide means it's a compound that has 2 hydrogen, 2 oxygen. They can write it this way, or they can write it this format, or they can write it like this. So anyhow they choose to write it, to actually be aware. The next one is alkyl peroxide. Now alkyl group has a general formula of R. So you can see something like this. You can see something like this. Or you can see something like. Now what is this R? Let's assume this R is a methyl group. If R is a methyl group, this becomes CH3 2O2. This is one of the ways they can write it. So once you see this on top of, well, I'm going to show us an example. We also have CH3, OOCH3. This is very different from what I gave us earlier. In the previous example I said, once you see something like this, just know this is an acid. It's acting as a catalyst. So don't mistake this for this. Peroxide must always have 2 oxygen at the center and on both sides flanked by the same thing. Hydrogen is flanking this 2 oxygen. Alkyl group is flanking this 2 oxygen. That's why it's called peroxide. Here, yes, we have 2 oxygens, but we don't have the same thing flanking it on both sides. So that is not a peroxide. Let's look at this example. Sometimes they can just write peroxide on top of this. This is an option. Or you can come here. once you see peroxide, this guy is unsymmetrical alkane, this guy is unsymmetrical reagent, unsymmetrical alkane, and there is a peroxide. There are various ways this question can be asked. You can just use word format. What is the product of the reaction when HBr reacts with so and so alkane in the presence of peroxide? Or they will say this reaction will follow Markovnikov rule, true or false. Now you look at the reaction, there is no peroxide, true. If there is peroxide, false. You can see this is now what we call word problem. The word, they are now twisting it. Sometimes you can actually understand what they are asking, but the logic behind the word problem will throw you off balance. So in this case now, this reagent is unsymmetrical, this alkene is unsymmetrical. The H goes to the carbon with more hydrogen, the Br comes to this other guy. So if I put asterisk here, this is carbon 1, carbon 2, and carbon 3. Now normally in Markovnikov rule, the H will have come to this guy, is it not so? Yes. But in anti-Markovnikov rule, the H goes to the carbon with less hydrogen, and that's carbon 2, right? Yes. This becomes CH3, CH2, CH2, Br. Now if you do this second guy, we have carbon, this is 1, 2, and 3. The H of this guy would have come here if it was to be Markovnikov, right? But since it's anti-Markovnikov rule, because of, do you know this peroxide, right? The H goes to this carbon 2. So this becomes CH3. So let's end this guy. Now this is propane or propene, and this is 1 bromo propane. So this is 2 methyl propane. Alphabetically, bromo is going to come first, so this becomes 1 bromo, 2 methyl what? Propane. So that is that with HBr. Please, if you're here and you've not subscribed to our YouTube channel, please do us a favor. Now let's look at water. Please put down. Water reacts with alkenes to give alcohols. Water reacts with alkenes to give alcohols. Water is an unsymmetrical reagent. As such, when it reacts with another unsymmetrical alkene, you must follow the Markovnikov rule. Now, we have an example here. We have CH3 and this guy is propene. Now, carbon 1, carbon 2, and carbon 3. Carbon 1 and 2 are the 2 carbons of the double bond. This guy has 2 hydrogen, this guy has 1. As a result of this, they are unsymmetrical. This guy, if you split water into 2 halves, what you're going to have on one side is not the same as what you're going to have on the next side. As a matter of fact, this guy is going to follow the Markovnikov rule. Alright, so the H of the water will come to this through carbon with 2 hydrogens. The OH comes to this other side, and this becomes CH3, CH, OH, CH3. Now this is propane 2-ol, and this is propene. Now another example of reaction of alkene with water, we have 2, 1, 2, so with 1, 2. Carbon 2 and carbon 3 are the 2 carbons of the double bond, and those 2 carbons have an equal number of hydrogens, thereby making it to be unsymmetrical. Now the question I'm asking is, Where is the hydrogen of the water going to add to? Is it carbon 2 or carbon 3? It's going to be carbon 3 because this guy has hydrogen, right? So this guy does not have. This can only work. This hydrogen would have gone to carbon 2 if it was what? Antimagnetic. Take note of that. So we have CH3. So if you want to name this guy, right, to start from here, please, any compound that has OH as the highest functional group, we name it as alkanols. 2 methyl, 1, 2, 3, 4, 4 carbon alkane is supposed to be butane. You now remove the E, the all is at number what? So we have 2 methyl butane, 2 all. So we are done with reactions with water. We're going to talk about reactions with hydrogen, reactions with halogen, and then we enter oxidation. Enter oxidation. Please don't pop ask question yesterday. Now with hydrogen. Now, this guy is called hydrogenation of alkenes. Right? If alkenes react with hydrogen, this guy is symmetrical, so there is no rule. 3 CH. Please, once any one of them is symmetrical, there is no rule. You can choose to add the reagent to any carbon of the double bond, you're going to be correct. Hydrogen is already symmetrical, so you don't even have to stress or bother yourself about it. Anywhere you choose to put the hydrogen is good to go. So the 2 carbons of the double bonds, they are unsymmetrical, but this guy is symmetrical, so it does not matter. So the hydrogen can go to any of the carbons, so this becomes it's just like saying, just like somebody saying if you want to spell school, this O should come first before this other one. Right? The correct one, how to spell school correctly is when this O come before this. Does it make sense? Exactly. So that's the same thing that is happening here because the same thing is added on both sides. Alright? So we have, so this is propane and propene. So I don't intend to take much example on that. The 2 previous examples has created the basis for. So let's look at the first guy. Reaction with halogen. Now where X can be Cl, Br, or iodine. Okay? If I come here, I will say CH3 plus Br2. This gives us, if I split this guy, Br, one comes to this guy, one comes to this other guy. Right? If you actually want to put it here first, it does not matter. O to be found. Alright, so this becomes this. The name is actually of interest to me. Now this guy is going to be 1, 2 dibromo because you're counting from the side that will give the substituent the least possible number. So here becomes this carbon 1, this carbon 2, and this carbon 3. So we have carbon 1 and 2 dibromo propane. So we are done with addition reactions of alkanes.